Okay, so now we're modeling population growth, and first let's have a little intro page for once. What's the basics of these models? So I'm not gonna for dp/dt equals r times p. This is gonna always end up very similar to our exponential. When we did separable equations, we had exact. This is pretty much gonna always end up in a very same spot. So I'm not gonna show the work for this every time anymore. Like not for this part for when we do Malthusian. I'm just doing it right here, a quick summary of it. So we have R equals reproductive rate, and we have P, which is population at time T. P at T, will eventually be our thing for population at time T, and we have just reproductive rate is the main thing to worry about. So you do separate the variables, so you get dP over P and R times, integral dt. You take the integral of these, of R dt and dP over P. And you get natural log of P of absolute value equals R times T plus a constant. After you combine the two constants into one. Then you get absolute value of P equals ER times T plus C. Without even having to worry about things, you can just drop the absolute values. Really, you can drop it for another reason besides before. Because basically the population will never be negative. That's something that can't happen, so you can just drop absolute value bars for that reason alone. Just a note. So that's why in P equal to ERT times E to C. We haven't done anything plus. So P at T equals C times E to the RT when we do our constant conversion, because exponential raised to a constant will be a constant. And P of 0 equals C times E to the R times 0, which is equal to P of 0 also. So our initial population is at P0 when time equals 0. So C times 1, because E to 0 is 1. Equals P0, so just C equals P0. So we could write this model for a couple problems right away as P at T equals P0 times E to the RT. Now on an exam, just do the steps, do a quick rundown of these steps like similar to this. It doesn't take up all that much space, and it's a good thing to just show at least some basic work of it. Even if you're strapped for time, just do a quick sketch of it. Just kind of like quick time-saving model. At least 3 or 4 steps just show that you understand how you get this model. And that way, all you have to do is remember dp/dt equals r times p, and you can quickly solve that separable equation. It's easy to remember. dp/dt equals r times p is a very easy thing to remember, I think. Change in population with respect to time, is just the rate of the reproductive rate times population. So logistic model is something that we don't, I'm not going to show how to solve it. You can see this in a classroom or a video. You can make a video just discussing how it's set up, how you set up this model and also solve it. It's a little bit of a tedious process and not worth going over in detail right now. But a logistic model on an exam, you can be sometimes given it. You'll be given, especially P at T, but sometimes even this included before. Basically, the solution's what matters. Yeah, you can be given as dp/dt equals r times 1 minus p over k times p. K is carrying capacity in this model. C is just a constant, and R is reproductive rate, like before. Yeah, carrying capacity is what is the basically the leveling off point where the population won't grow. It'll basically have at t equals infinity, as time goes on forever. That's what it should stabilize at, ideally in the logistic model. It'll eventually fall to that, it'll rise to that level, not go any further, any higher. But yeah, P at T equals K times C times ERT divided by 1 plus C times ERT. And yeah, but the problems with the Malthusian model are pretty straightforward, especially even with this, it still would be pretty short. Let's make sure it fits in one page, though, just not having to redo this four times, but 4 examples that are relevant. But that being said, a little introduction. A biologist starts with 100 cells in a culture. 24 hours later, he counts 300. We assume Malthusian model. What is the reproductive rate? What will be the number of cells at the end of 5 days? So even though it's lots of hours, this is definitely a model we do in days. So each day is a t unit. So t equals 1 is 1 day, t equals 2 is 2 days. So 100 cells, 300. So P0 times e to the rt is what our population at any time t is. P of 0 equals 100 and P of 1 equals 300. Ignore this scribbles. The official solution wants it in days. I did it in hours, but I scribbled out. You can do this in hours though if it's not explicitly asking for it. Just make sure you note hours you're doing this in terms of hours for reproductive rate instead of days. That being said, so P of 1 equals 300 equals 100 times e to the r times 1. Because P of 0 is already known as 100, we know that just plugs in. So at P of 1 it's equal to 300, which is, so P of 1 is equal to 100 times e to the 1 is t, so times r. And we're trying to find reproductive rate. So 300 equals 100 times e to the r. We just divide by 100 to get e to the r equals 300 divided by 100. So this is e to the r equals 3. We take natural log both sides to get r equals ln 3. And that's approximately equal to 1.0986. I add in the unit day to -1 just to distinguish it. It's like it's a rate. So it's per day. That means per day. But it's just a way to know that units cancel out since time is in days. In the top, since you take e raised to something, you want it to be unitless. That's a general rule of thumb, especially in physics, known that you want it to be unitless when you take something like that. So, and then we want to know what the number of cells at the end of 5 days is. So that's P of 5. So that's equal to 100 times e to the 1.0986 times 5. So for that you get 24,298.5. And you should round down because of how things are. You need it rounded because you can't have half a cell. At least I mean you could, but it wouldn't be alive, pretty much. So 24,298 cells after 5 days. Similar problem here was the same Malthusian model. We have 1 day of gross. We start off with just knowing 1 day of gross, it's 1,000 cells. 2 days of gross, 3,000. We assume a Malthusian model. What is the reproductive rate and how many cells are present initially? So we need to find R and we also have to find P0. This is an interesting type of problem because we don't know our initial population, but we know it after 1 day and after 2 days. So P2 equals 3,000, which is equal to P0 times e to the 2r, and P1 equals 1,000, which is equal to P0 times e to the r. We have equation 1 and 2 here, I colored them. And we divide 1 by 2, and we have 3,000 divided by 1,000 equals P0 e to the 2r divided by P0 times er. And some things cancel out. P0 cancels out, obviously, the initial population. 3,000 divided by 1,000 becomes just 3. It neatly changes in that. And e to the 2r divided by e to the r is equal to e to the 2r minus r. So, and 2r minus r is just r, so it's e to the r equals 3. You take natural log both sides, you get r equals ln 3. And so r equals 1.0986 to e to the -1. So same reproductive rate as the last one, I believe, right? Now all we have to do is find what the initial population is. So we just solve one equation for P0 as a way of doing this, at least. There's one way. So 1,000 equals P0 times e to the 1.0986, because it's just 1 times that, so it's the same thing. It's e to the r. So 1,000 equals P0 times 3. Because yeah, we know e to the r is just 3, so. But no, P0 equals 1,000 divided by 3, and we divide both sides by 3, and we get P0 equals 333.33, which is about 333 cells. So 333 cells were initially present. So we have a population of bacteria is growing according to the Malthusian model. If the population triples in 10 hours, what is the reproduction rate? How often does the population double itself? So we're given very little information here. But we're actually given quite enough information. We're given enough information, that is. We're given quite a lot of information, meaning we've given enough. This gives us more information than one thinks. You have to read it carefully. Population triples in 10 hours. What is the reproduction rate? So what we know is P of t equals P0 times e to the RT. We have P of 10 equals 3 times P0, equation 1, and equation 2 we can say is P of 10 is also equal to P0 times e to the 10R, because the population triples. So any population will triple in 10 hours. The population will always triple. So that means the initial population tripled in 10 hours. So 3 times P0 is equal to P of 10, and P of 10 is also equal to P0 times e to the 10R, because t is 10 here. So we equate both equations, and we get 3 times P0 is equal to P0 times e to the 10R. We can divide both sides by P0 to get e to the 10R equals 3, and then take natural log to get 10R equal to ln 3. And divide by 10 both sides, the r equals ln 3 divided by 10. And we plug this into a calculator to get 0.10986 hour negative 1. And it's given in hours this time we're doing it. And we want t now for our second part. How often does we want a time for how often does the population double itself? So want t such that P of t equals 2 times P0, so it doubles the population. So 2 times P0 is equal to P0 times e to the RT, and we cancel out P0 both. Yeah. Because we know what R is, but first we set it up, so we'll plug in R when we're ready. But first we just set up, so P of t equals 2 times P0, and that's equal to, in general, so P of t is equal to P0 times e to the RT, in this case, for one of those. So 2 times P0 equal to P0 times e to the RT. P0 cancels, so we get 2 equals e times to the RT, and R is substituted in. Take natural log of both sides to get 0.10986 t equals ln 2. T equals to division, so basically divide both sides by R here. So we get t equals ln 2 divided by 0.10986. And you plugged in the calculator and you get 6.309 hours to double itself. So we have one more problem with the Malthusian model. Population of bacteria growing according to the Malthusian model doubles itself for 10 days. If there are 1,000 bacteria present initially, how long will it take the population to reach 10,000? So we want to reach 10,000. It doubles itself in 10 days. So all we have to do is we have to find reproductive rate as the first thing. So P0 equals 1,000. Doubles itself in 10 days. So P of 10 equals 2 times P0 is equal to P0 times e to the R10. And like before, we can just divide out P0, so it doesn't really matter. So it's 2 equal to e to the 10R. Natural log, we get just 10R equals ln 2, so R equals ln 2 divided by 10. R equal to 0.0693 to e to the negative 1 power. So it's per day. And P of t is equal to 10,000 is equal to 1,000 times e to the RT, which is 0.0693 t. No. And we have to solve this for t. Because we want to know, we want t when P of t equals 10,000. Because we already have our reproductive rate, we can just solve for t in this case now. So we divide by 1,000 each side, we get 10 equals e to the 0.0693 t. Natural log of both sides, so it's ln 10 and 0.0693 t. Then we have t equals ln 10 divided by 0.0693, and plugged in the calculator, you get 33.23 days, approximately 33.23 days it'll take for it to reach 10,000 species, number. The number will be at 33.23. It's 33.23 days to get 10,000 bacteria. That's what I'm trying to say. Okay, enough of Malthusian model. Now it's time for 2 examples of how to mess with the logistic equation. So we have a population obeying the logistic equation begins with 1,000 bacteria. Then doubles itself in 10 hours. The population observed eventually to stabilize at 20,000 bacteria. So that's our K value, is what it stabilizes at, is what they often can word it as. Or will level off at. Many different terms mean the same thing. That's carrying capacity. So we find the number of bacteria present after 25 hours and the time it takes the population to reach 1/2 of its carrying capacity. So K equals 20,000 and P0 equals 1,000. We have this model here. So what we first do is have to find what C is equal to in this type of problem. And that's a slight challenge in all these because we have to go through the mechanism. So P of 0 is equal to 1,000, which is equal to 20,000 times C times e to 0 divided by 1 plus C times e to 0. So at least E cancels out to 1. It just becomes 1 times C. 1 times C. So 1,000 equals 20,000 times C divided by 1 plus C. You know, C changes depending on the conditions, initial population and such, so we have to go through this every problem. So when we divide by 20,000, and oh yeah, I see what I did. Yeah, better to leave as fraction for these types of problems. You might as well leave some things as a fraction for the time being, and eventually you can put them in a calculator for your calculations. But at least for the time being, and you'll see why. Things get messy, so you want to keep things as simple as possible till a while in. So yeah, so C divided by 1 plus C from, ignore this, but this is a way of doing it in fraction form and all that stuff. I mean decimal form. So keep them in fractions. So 1,000 divided by 20,000 equals C divided by 1 plus C. So 1 over 20. 20,000 divides by 1,000 20 times, and 1,000 divides by 1,000 once, so 1 divided by 20. So we cross multiply now easily. So 20C equals 1 plus C, and 20C minus C equals 1, so it's 19C equals 1, so C equals 1 divided by 19. And you have a calculator, you can write some, you can do alpha, a symbol, and you can get a fraction and it will simplify automatically. If you plug in the numbers, it'll give its simplest form automatically on any graphing calculator, any modern one at least. So that's just something to consider. It's easy. It's good to keep them as a fraction. I realized after, so I added that in. Okay, so next part. We have P of 10 equal to 2 times P0. So it doubles in 10 hours. That's what I'm writing here. And that's also equal to 2 times 1,000, because P of 0 is 1,000, so it's equal to 2,000. So P of 10 equals 20,000 times C times e to the 10R divided by 1 plus C e times e 10R equals 2,000. So we divide by 20,000 and get 2,000 over 20,000, and that simplifies down to 1/10. We have this on the left-hand side here. So we cross multiply. And I'm leaving C as it is. We'll add it in later on. But you should probably do it like this, at least when you're first starting out, to not get confused by all the terms and to make it so you can fit more, not have to rewrite so much complicated stuff. So 10 times C times e to the 10R equals 1 plus C times e to the 10R. We can subtract both sides, C times e to the 10R, and then make it 9 times C times e to the 10R, because everything's the same, but it's combining like terms basically, like in algebra. So it's 9 times C times e to the 10R, which is equal to 1. And that means e to the 10r is equal to 1 divided by 9 times c. Take natural log of both sides to get 10r equals ln of 1 divided by 9c. Divide by 10, you get r equals ln of 1 divided by 9c. Divide by 10. You plug in c, which is 1/19 to you. 9 times 1/19 to know, so it becomes 1 divided by 9/19. Natural log of all that divided by 10. And 1 divided by 9/19 is just 19 divided by 9. Natural log of that divided by 10, you plug it into calculator, you get 0.07472. And it's not asking for reproductive rate, so it doesn't matter. But we need it to find the questions. So we find after 25 hours the number of bacteria. P of 25 equals 20,000 times 1 divided by 19. We just plug in all the values times E raised to the 25 times, You basically plug in everything including t equals 25 since it's p of 25 and solve in a calculated this complicated expression. And you get 5,083.61, which is about 5,084. So 5,084 bacteria present after 25 hours. Or you could round down, either, But still, I don't think that's the biggest concern. Probably should round down because these are organisms and all that. But if you got that far, you'd lose like a point or half a point at most. Wouldn't be the biggest issue. And now the carrying capacity is the important part. So we want to find the time it takes the population to reach 1/2 of its carrying capacity. Okay, so that's 1/2 times k is equal to 1/2 times 20,000, which is equal to 10,000. So P at t equals 20,000 times C ERT divided by 1 plus C ERT, which is equal to 10,000. We want to find t, so I wait to plug stuff in till near the end. To keep things simple to rewrite. Because it still takes up a lot of space, but at least this way it's more manageable. So we have this equation, 20,000 times C ERT divided by 1 plus C ERT equals 1,000. We divide by 20,000 both sides, so 10,000 divided by 20,000. Simplify that down to the fraction 1/2. And then we multiply, cross multiply, so it's 2 C ERT equals 1 plus C ERT. So we subtract C ERT on both sides, we get C ERT equals equals just 1. So divide by C, so 1 C ERT equals 1 C. 1 by C. Then we take natural log of both sides. We get RT equals ln of 1 divided by C. Divided by R, we get T equals ln 1 divided by C divided by R. Plug in 1 divided by 19 for C. So 1 divided by 1 divided by 19 will become 19, ln of 19. All divided by 0.07472. And plugged in a calculator, you get 39.41 hours to reach 1/2 carrying capacity, and that's our answers. So not too bad. And we have one other example that's good to look at. We have a logistic equation with eventual population 20,000. So again, carrying capacity 20,000 this one. We have initial population is 1,000, and 8 hours later, the observed population is 1,200. So it didn't increase as dramatically as the last one, I don't think. So reproductive rate will be a little bit different for this one. Find the reproductive rate and the time required for the population to reach 75% of its carrying capacity. So we're just finding R and the time required for the population to reach 75% of its carrying capacity this time. Which is obviously going to be just 15,000 out of 20,000. So 15,000. We'll see that later, but first we have to find R in order to solve anything else. Similar to the last one, we have so P of 0 we start with is equal to 1,000, which is equal to 20,000 times C times e to the 0, divided by 1 plus C times e to the 0. Just becomes 1,000 divided by 20,000, we divide both sides with 20,000, all equal to C over 1 plus C. And that can be simplified down to 1 divided by 20, equal to C over 1 plus C. So this is C is equal to 1/19 like the last one. Not the best, but that's because the initial population is pretty much the same as well as the carrying capacity, so it's going to happen like this. So the same process before you get 1/19 for C. That being said, now it's time for some changes. After 8 hours, it's only 1200. So 1200 equals 20,000 times CE8R divided by 1 plus CE8R. And we solve for R this time. So 1200 divided by 20,000 equal to this expression, so it's 3/50ths. You put it in the calculator, it gets 3 divided by 50 on simplification. Then we cross multiply, so we got 3 times 1 plus CE8R equal to 50 CE8R. So subtraction again like before, so it's 47 CE raised to the 8R power equals 3. Divide by 47C, take natural log, divide by 8. So you get R equals natural log of 3 divided by 47C, all divided by 8. Now we can plug in for C and solve for R. So 1/19 times 47 was be 47 divided by 19. We still have other things as before. Doing this, you can do this all by hand up to the point when you have to take natural log. That's why I show it sometimes. So 3 times 19, because 3 divided by 47 divided by 47/19 basically. That's equivalent to 3 times 19 divided by 47. So it's 57 divided by 47. You take natural log of that. Then divide that by 8. You get 0.02411 reciprocal hours. So it's per hour. So P of T is equal to that. And we have C equals 1/19, then R equals 0.02411 hours, negative 1 hour. And we just have to find now 75% of K, 15,000. We have to find the time it takes for that. So 15,000 equals 20,000 times CERT divided by 1 plus CERT. Knowing what C and R equal, we can solve this now. So we eventually get 3/4. Kind of expected when you do 15,000 divided by the carrying capacity. And now we have to start the process. So we cross multiply again. 3 plus 3 CERT equals 4 times CERT. Subtraction to get CERT, just CERT this time because it's 4 minus 3, so 1. So equal to 3. Divide by C, take natural log, you get RT equals ln 3 divided by C, and then divide by R both sides, you get T equals ln 3C, 3 divided by C, all divided by R. And plug in R and C together, slowly solve. So 3 divided by 19 is 3 times 19, so 57. That's all so natural log of 57 divided by 0.02411. Put it in a calculator, you get 167.69 hours for the population to reach 75% of its carrying capacity, so it takes a while. Is basically what is the answer. Is that this takes a while. And that's it for this section on population growth, modeling population growth using differential equations, and that's all.